Let me introduce you. So this talk is an uninvited talk. So the next speaker is Dr. Chia-Min Chung. He is going to tell us about stripe and superconductivity in the two-dimensional Hubbard model. So please.
Yeah, thank you. So this talk will not be a new tensor network method, but instead I would use just traditional DMRG and applying on a specific problem and see, like, it should be a series of work and see how far we can go by using this, DMRG. And the problem we are considering is a two-dimensional Hubbard model on the square lattice, on 2D square lattice. And the model is represented by this Hamiltonian. Then it has only two terms. So one is the hopping, that the electron can hop in this square lattice, and it can lower its energy by hopping. So the electron want to hop as much as possible. And the other term will be the on-site interaction U. It's saying that if two electrons sitting on the same site, then it would rise this energy by U, which means that the electron does not like to, sitting on the same site. And our task is to find out the ground state of this model, and also to understand the ground state properties, like what is its spin order or its charge order, or whether the ground state will have superconductivity. And even this simple model, and with this simple task, turns out becomes a very difficult problem because of strong interaction and strong correlation in the system. And so we have been working on this for a series of work, and these works are mainly collaborated with like Minpu Chi in Shanghai Jiao Tong University, and this work is highly collaborated with quantum Monte Carlo guys. So it's not only DMRG, but also a lot of quantum Monte Carlo simulation involved, and also more senior guys like Xu Zhang, Steve White, and Uli Showalk. So these are the Monte Carlo guys, and those are the tensor guys. All right, so the motivation of studying this Hubbard model is to understanding the superconductivity in cuprate high-TC superconductor. So the typical structure of cuprate, they have this, like a different material, we all have this 2D plane, which is copper and oxygen plane, which is believed to be most important for the superconductivity. So the simpler model to understand this material would be modeling this 2D square lattice. And if we consider only the copper side, then it would be just a square lattice. If we further consider only the contact interaction, like the shortest range interaction, then we have only interaction U. Then it turns out to be the single band Hubbard model. And as I said, there's only only two terms, and there are only two parameters actually. So one is the ratio between U and T, and the other is the doping, or is the electron density in the lattice. So here we say zero doping means that the system is at high filling, which means one particle per site. And in particular, we consider whole doping, instead the density is lower than 1. And the experimental phase diagram of cuprate, that typically is like this. So here is the doping versus temperature. And at zero doping, or at high filling, the ground state would be the antiferromagnetic state. And this is the easiest point we can understand. It's the easiest point in experiment and also in the numerical simulation. So almost all the methods get a consistent result here. And then if you increase the doping, then the system goes a phase transition to a superconducting phase. But the recent experiment showing that it's not only superconducting state, but it's also some kind of other orders, like charge density wave orders, and also spin density wave orders. So it's pretty complicated inside this superconducting state. And it is believed that this kind of competing order or like different orders in this region plays important roles in this so-called pseudo gap phase, which is crucial to understanding superconductivity. So now the problem is not only to have a model to understand to have a superconductivity, but also it should also showing these different orders and this competing of low energy state. Yeah, and this kind of charge density wave in particular, we consider this mixing of charge density wave and spin density wave that we call it a stripe order that we will explain more clear later. And these orders are observed in different experiments, and also this even the superconducting pairing has some kind of finite wavelength pairing, so they also have sphere density wave orders. So there are several kind of different order competing here. So the question is whether this simple Hubbard model can capture this physics in the material, and this problem has been explored for a long time, and there's tons of all kind of answers in the literature, and it's very difficult to get a consistent result from different methods. It turns out that the different bias from the method can lead to a completely different result. And also the cold atom experiment are trying to approach this problem, but they can barely lower the temperature to assess the antiferromagnetic state at zero doping, and and this temperature is still far from the superconducting below the superconducting critical temperature. So this also showing that this simple model is a difficult task, but why it is so difficult? A way to understanding this model is to consider a dope Hubbard model as a dope antiferromagnetic background. So we know that at zero doping, the system is in antiferromagnetic state, which means that, I think I made some mistake of the spin, but it actually, if you look at this 6 spin, it means that the nearest spin in the nearest neighbor will have opposite directions, or just these 4 spins. In a dope in the hole just means that we remove one of the electron and it can move in the lattice. So physically we think of a doped Hubbard model equals to a dope antiferromagnetic state. Now, if we from the classical picture, if we start from a perfect antiferromagnetic state and just remove an electron and then we try to move the hole to the right, we found that we introduce some high energy spin that you have parallel direction for the near response, and this would raise the energy, the system's energy, make the system unhappy. So, but the hole want to move as much as possible to lower the kinetic energy. So the text for the nature is to find a way to use the superposition to move the hole as much as possible, but at the same time to keep this antiferromagnetic structure as much as possible. And if you do this in the classical way, you found there are several ways to do it. And you can make a lot of patterns with very close energy. And nature would try to make a superposition of them to find, a clever way. And that basically why this system would be so difficult, because they are kind of spin frustration from the moving of the holes. Yeah, and this is also the reason behind it. That's why you have this so many energy, closed energy competing state. All right. So to solve this, to target this problem, we use, actually we use several methods to try to solve this problem. And in particular, I'm using, traditional DMRG in quasi 2D in, a standard way, like we snake a 2D lattice to 1D MPS. And due to the entanglement structure, that we can simulate a very long system, but very short width. And also we mostly consider a cylindrical boundary condition, which means that it's open in the long direction, but periodic in the short direction, such that, to satisfy the entanglement as much as possible. And in addition to DMRG, we also compare our results with, especially the quantum Monte Carlo. And also in the first work, we also compared to other two methods like IPAPS and DMET. And the good thing of this comparison is that this different method has very different systematic error. So for example, the DMRG, since we always converge to a high accuracy, it's on a finite size, we got a pretty accurate result. But we can only simulate on a small width. So the largest uncontrolled error for us is the finite size from the finite width. And from the quantum Monte Carlo, they have very different kind of error from the constraint path to eliminate the sign problem. So this, I'm not going to the detail, but it's nothing to do with the entanglement. And it's also not a variational method. It's a method based on the sampling. And it also favor different side of interactions. The DMRG works better in the large U, but Monte Carlo works better in the small U. So they're kind of, by using this orthogonal method, we're trying to get a consistent result. And by doing this, we're, we kind of will be most confident with our result. And in the first work, we also compare with IPAPS and DMET. They are also kind of tensor network method. And the biggest error would be from the finite unit cell or from finite cluster size. But fortunately, all of these methods are able to find the consistent ground state, which we call the stripe state. So this is a unit cell for a stripe state. So here, the circle is proportional to the hole density. So the larger circle means larger hole density on this side. And the size of the arrow is proportional to the spin expectation value. So from this unit cell, you can see there is a charge density wave from this oscillation of the hole density. And also you can see a spin density wave that you see these anti-ferromagnetic patterns, like in here. But also these two orders are coexisting in an interesting way that you see the hole concentrate in a specific position, and the holes goes in one of the direction. So if you copy this unit cell to a 2D plane, you see this hole split to several lines that we call them several stripes, like going here or there. And this stripe or this hole plays as a domain wall for the antiferromagnetic domain. So you see the antiferromagnetic pattern actually flip the spin when it's across a stripe. So this spatial way of charge density wave and spin density wave together, we call it a stripe order. And this kind of stripe order has been observed a long time ago by Stephen White in TJ model. But in this work, we are able to, we found different wavelengths, and we are able to make it consistent from different methods with with a small energy difference. So yeah, so this is we are quite confident at this point that the true ground state of the Hubbard model is this, we say, the vertical stripe. And also other computing states are also found in this IPAPS or DMVT method, including the uniform superconducting state and diagonal stripe. It's the whole goes in diagonal direction. And the energy difference between this exciting or this computing state to the vertical stripe is very small. It's only 0.01 T, right? And to understand why the stripes is a good state, is a good low energy state, here's a cartoon picture. So as I said, that we consider a doped hole in an antiferromagnetic background. If we move the hole, then it would introduce some high energy spin. Now, however, if we have two holes together, and if we move these two holes to the right, then we found that the antiferromagnetic background is recovered again. So in this way, the system would be happy. However, if we move the holes in another way, then it still has this high energy spin. So a clever way to do it is to align the hole in one of the direction to form this this stripe, and we have different domains in between the stripe. And now the holes or this stripe can freely move left and right without messing up the antiferromagnetic patterns. So in this way, the system can make money, the system can lower the kinetic energy by moving the holes, but also it would not increase the spin, antiferromagnetic spin too much. Right, and it is also interesting to see that actually there's already kind of parallel mechanism in this picture that although the Hubbard model is a purely repulsive model, but there can be a mechanism that the hole want to go together to recover the antiferromagnetic pattern. All right. Now we already see that there are different computing state to the vertical stripe, but even for the stripe state, they are also a very close energy state. Let's say if we have totally 12 holes in the system, then we can either split them by 2 stripes, and each stripe will have 6 holes, or we can split them to 3 stripes, and each stripe will have 4 holes. So these two systems are exactly the same system with the same coupling and the same density, but actually we can stabilize these two very different states in DMRG, and we found that their energy is extremely close. And this is also observed in almost all the methods we consider, that the stripe of different wavelengths are almost degenerate in this region with wavelength from 5 to 8. So it's not only the competing between the stripe and the uniform superconducting state or diagonal stripe, is the stripe itself is a strongly competing energy. All right. So now the next question. So now we have understand that the stripe is the ground state of Hubbard model, and the next question is naturally that does this stripe stay superconducting? And also even this is not an easy question to answer. So to answer this question, we consider two kind of approach. So one is it's more straightforward, that we consider a long system, a long cylinder, and we measure the pair-pair correlation. So the pair-pair correlation is defined by this. So this delta is nothing but a singlet annihilation operator. So you annihilate a singlet from a bond. And if the system is in a long-range superconducting state, then the pair-pair correlation should at least decay in power law, because we are working in quasi 1D, so power law decay would be kind of the longest correlation we expect. And another way to approach this problem is to apply a pairing field that we basically add additional term in the Hamiltonian, which is basically just proportional to this delta, just to make it Hermitian, so it plus a delta Dagger. So when you apply this term in the Hamiltonian, then it would enforce the system to have superconductivity. And then we study like how the induced superconductivity change when we decrease the pairing field to the zero. So we basically asking that what is the response of the system to the superconductivity or to this pairing field. So this is the same to say that we apply a magnetic field to induce magnetization and see whether this magnetization persists when you have zero magnetic field. And of course, this is only possible when we consider infinite system. Right. So in the first part, we use TMRG to simulate a long cylinder, and then we study the pair-pair correlation. And the first thing to observe is the pairing symmetry of the system. So in high TC, we expect the system or the pairing should have this D-wave symmetry, which means that the correlation between the vertical bond and the horizontal bond should be symmetric, but with a different sign, with an opposite sign. So it stays true for all the vertical bond and horizontal bond. And this is indeed what we observed in this panel, that this black circle is the correlation between the vertical and the vertical bond. And the red curve is the correlation between the vertical and horizontal bond with a minus sign, with an opposite sign. And you see that if we apply a minus sign, then they becomes perfectly symmetric. So this tells us that the system, the pairing symmetry in the system is indeed the D-wave symmetry we expect. However, the correlation, the decaying of correlation showing the exponential decay, and it actually decays pretty fast. It's only on the 40 side, it decays to 10 to the minus 8. So it's showing that although the system have the right symmetry, but this correlation is actually a short range, which means that the system does not truly a superconducting state. And then we use the other approach, which basically tells us the same story. So in this case, because we already know the pairing symmetry, so then we apply the D-wave pairing field to globally on the system to induce the pairing order, as shown here. So here the HP is the magnitude of the pairing field. And then we study what is the pairing order when we decrease the pairing field to 0. And this is mainly done by the Monte Carlo, because the Monte Carlo can do it in very big system size, so they can extrapolate to thermodynamic limit to make this analysis possible. Then we found that if we decrease the pairing field, then the pairing order also decrease continuously to 0. So this also confirmed that at the thermodynamic limit, the system is not a long-range superconductivity. And you may wonder that this analysis, this might just due to the finite size that you always get zero order, because on finite size you don't have a symmetry breaking. But if you do the same analysis on the magnetic field, the magnetic order, so you apply a magnetic field, and then you decrease the magnetic order to, to see what is the magnetization at zero field, then you get a pretty good behavior all the way to the zero field. In this zero field magnetization is perfectly consistent with the pure quantum Monte Carlo method. So this is actually a pretty good way to analyze the system. All right. And we also, here we're just showing that actually the superconductivity is competing with the stripe state. So here the blue curve is the superconducting order, and the red curve is kind of the stripe amplitude, or how strong of the stripe order. And you see that whenever the superconductivity becomes stronger, then the stripe order becomes weaker. So they're most likely they're competing with each other. All right. So to give a brief summary about the Hubbard model, the first thing is the ground state stripe. And then the stripe has D-wave symmetry, but the pairing is only short range. So it's not really a superconducting state. But more importantly, we found many low energy competing state, which means that the ground state of Hubbard model is kind of sensitive. So if we kind of add additional terms that could be relevant in the experiment, it's very likely that the ground state will change its property, and maybe we just change to a superconducting state, the consistent with the experiment. So the next step to consider this problem is to consider an additional term in the model. And usually the most important term would be this next nearest neighbor hopping T-prom, which is this cross hopping. So now the electron can not only hop in the square lattice, but can also hop in this diagonal direction. Right. So this T-prom Hubbard model was also studied by IPEPS, and in IPEPS, for the negative T-prom equals to 0.2, they found that there's actually a finite superconducting state in the doping around, from 0.15 to 0.25. And they also found the coexistence with the stripe order, although it's a bit weaker, and also the pairing symmetry is D-wave. And there's another important work about this T-prom Hubbard model is from Hubbard Chung, that they use DMRG to study this T-prom Hubbard model on a width-4 cylinder. So on this width-4 cylinder, they found that when you consider a T-prom, then the spin density wave now becomes short range. So now the spin density wave correlation decays exponentially, which means that the system does not have spin density wave order, and the charge density wave persists. So there's still a charge density wave, but more importantly, now the superconducting correlation becomes power law decay. So this is pretty, this is pretty encouraging, because now we get more consistent result with the experiment, that we have only charge density wave, and we get kind of quasi-long range superconducting order. However, I emphasize that this is done by width-4 cylinder, because one need to in particular careful about this geometry. So we study this the same system, this width-4 cylinder, also by DMRG, and discuss the pair-pair correlation more carefully. And we found that the pair-pair correlation showing that the parent symmetry in this system is actually not the ordinary D wave that we expected. But you remember the ordinary D wave, you have opposite sign for all the vertical correlation and the horizontal correlation. But here instead, we found this kind of parent symmetry. So you see, now if we consider the correlation of this black vertical bond to all the blue vertical bond, it is shown here by this blue curve. And then the correlation between this vertical black bond to all the red vertical bond, it's showing this red curve with, I'm sorry, it's the correlation with the minus sign. So you see now the correlation the correlation to this blue bond and to this red bond, they are perfectly symmetric, but they have different sign. So it's more like in this way. So you have different signs from alternatingly in this vertical direction. In the correlation to the horizontal bond are basically exponential decay, so which showing that there's very weak correlation to the horizontal bond. So this kind of new parent symmetry is not as we should expect it, but then we understand that this correlation is also not so surprising, because a width-4 cylinder is a very special geometry that if you look at this in the more 3D point of view, say you have a width-4 cylinder, width-4 means that you have only 4 sides in one of the direction, and you have periodic boundary condition. So you just wrap around this 4 side, and you found this width-4 cylinder is actually just a stack of plaquette. So yeah, so if we say that this 4 side as a plaquette, then you just like a chain like formed by a series of plaquette. And the ordinary D wave in this 3D view would be like the D wave superconductivity on the surface, like would be like wrapping on the surface. However, the other parent symmetry we found in this 3D view is more like a D wave on the plaquette. So the D wave means that you have different sign on different on the vertical and the horizontal direction. So if you just look at one single plaquette, it's also like different sign between the vertical and the horizontal bond. And you can think of that now the D wave only happens on each of the plaquette, and the system becomes kind of effectively 1D system. And we think this is the reason that's why you would then have this quasi long range superconductivity. So now the rule of the T-prom to the superconductivity becomes a bit tricky, because now it's more, because in this 3D point of view, then the T-prom, this cross hopping applies only on the surface of the cylinder. So it looks more like that you apply this T-prom on the surface, and then you push the superconductivity from the surface to the plaquette. So this is actually, this picture is kind of consistent with the old study by Stephen White, that they found in TJ model that the negative T-prom actually suppress the superconductivity, while the positive T-prom would enhance the superconductivity. Right. So to further test this idea, that we consider a system that we have T-prom, we have this cross hopping only on the plaquette, but not on the surface, and to see that whether this would push the superconductivity back to the surface. And we actually found this is actually the case, that if we consider this kind of system, then the parent symmetry going back to the ordinary D wave, saying that the vertical correlation, the correlation between the vertical and horizontal bound have opposite sign. And also, also the horizontal correlation is compatible with the vertical correlation. Now then we provide this kind of rough phase diagram that if we consider different strength of this T double prime on the placket and the T prime on the surface, and we find that with the larger T double prime, the placket parent kind of pushing back to the larger T prime. So this kind of showing that this T double prime kind of trying to stabilize the surface parent. So this is more like the cross hopping kind of push the superconductivity away from the placket, right? And this kind of placket parent, it was actually also observed in the TJ model, but at the TJ model, the placket parent exists even for 0 T prime. And if you consider a positive T prime, then it goes a transition from the placket parent to the ordinary parent. So this is also consistent with our observation that then you have positive T prime to enhance the hopping, but the negative T prime maybe would just suppress the hopping in this spatial geometry, right? And now, so far, we considered only the width for a cylinder, which has this spatial geometry. And so this will stabilize the placket D wave. But does this placket D wave or its extension, any similar parent symmetry can exist in a wider system? So to answer this question, we consider a width 6 cylinder and compare with the width 4. So here we apply 2 kind of parent field. So one would try to enhance the ordinary D wave, and the other would try to enhance the placket D wave. And we found that at the width for a cylinder, the response from the placket D wave would be larger than the ordinary D wave. So this yellow band is for the placket D wave, and this blue bar is for the ordinary D wave. However, if we consider width 6 cylinder, then you see the ordinary D wave response is much stronger than the placket D wave. So this is also not surprising that this spatial kind of parent symmetry is only spatial for this width for a cylinder. So we need to be pay additional attention. We need to be especially careful on this spatial geometry, right? All right. So this gives us a midway summary of this Hubbard model simulation that we first find out that the ground state of Hubbard model is stripe, but it's not superconducting. But whether we can start from here to get some superconducting state, for example, by fluctuating stripe, is still an open question. And then if we consider a cross hopping T prime, then on this spatial geometry or this spatial finite size, then we indeed get a long range superconductivity, but it actually has placket D wave rather than the original D wave we expect from 2D. So we need to consider a 2D limit. So this means that the finite size effect is very important, and we need to do a careful finite size extrapolation or some sort of finite size analysis on this system, and this is still an ongoing work. Okay, right. So just then, I feel that I should also show you some, some unpublished work that this is not definite conclusion, but here to do this, consider this T-prong on a larger cylinder, we consider both the positive T-prong and negative T-prong, and we found that it's pretty easy to find a stable superconducting state for the positive T-prong, but it's pretty difficult to get a good superconducting state in negative T-prong. And this is also kind of similar with what was observed in the TJ model. Like, for example, on the width 6 cylinder with positive T-prong, you can get this kind of perfect D-wave superconducting state. But with negative T-prong, you have this complicated pair, this pairing correlation. It's locally like D-wave, but you have noisy very fast in the long range. But this does not mean that it's impossible to get superconductivity in negative T-prong, because what happened for the negative T-prong is that it's strongly competing. There are many, like several states with extremely close energy. So this is negative T-prong, and with D-wave pairing field. And here we simulate not only the ground state, but also the first excited state and the second excited state from DMRG. Then they are not necessarily the true ground state or excited state, but at least there are 3 orthogonal states found by DMRG. And you found that there are, several competing states with extremely close energy and with a similar superconducting order, but they have very different response from the density when you apply a pairing field. So it is possible that the true ground state would be a superposition of all these competing states. And this is kind of, in a quantum Monte Carlo, they're kind of easier to find this finite superconducting state. And I think this is the reason that the negative T-prong is more subtle, but it's still possible that by mixing this state, you can have finite superconducting state. All right. So here I just list some of the challenge about this problem for the tensor network. So why this is so difficult? So the first thing is that you see this new length scale, which is the stripe wavelength introduced by the interaction. So it's not, although all the interaction are only on site, and the hopping is just nearest neighbor and next nearest neighbor, but you have this new wavelength of the stripe wavelength introduced by the interaction, and this makes you difficult to know like how large of the unit cell you need to consider, and also it's very sensitive with the finite size. So the finite size effect is important, and also there are many low energy states, so you need to be able to have a good accuracy to be able to distinguish this state. And also, of course, if we find a stable superconducting state, then the finite temperature transition to this state will be extremely important. So this will be like a few direction or few issues we will go in the future discuss. All right. So yeah. So I will stop my talk here, and thank you for your attention.
Thank you very much. So now this talk is open for the question. So do you have any questions or comment? Can I ask one naive question?
Yeah.
So you said that in the previous slide, so the true ground state, probably the superposition of these 3 or more states. So why you consider the superposition of them?
it is just a possibility that because in DMRG in DMRG it's not only trying to find the low energy state, but also try to find low entanglement state. So in a single DMRG simulation, it is likely to be trapped to a low entanglement state. So this is indeed the case we are finding here. So if we just do one DMRG simulation, we would get just this blue curve. But then if we say we want to find another low energy state, but orthogonal to this blue one, then we would get this orange one. So this will be another state with extremely close energy, which is shown here, but it's orthogonal to the first one. So if we consider the model or the Hamiltonian in this subspace of this just two-state subspace, we should be able to rediagonalize this Hamiltonian and probably find another, even lower energy state by making superposition of this two state. And this can be done by considering a set of state. So it's not necessary to be only two. So this is still doing. We are trying to find more and more state with close energy. And it could be that the true ground state will be a complicated superposition of that, but just the entanglement is so big that the DMRG just could not find it. Yeah. So so this could be a way that a simple DMRG calculation is limited, but we may, in using this way, we may still find a way to capture a high entanglement state.
Okay, thank you. So next, Henrik Dreyer, please.
Thank you for the very interesting talk. So at the end you mentioned the finite temperature, that at some point you will need to study the finite temperature to transition. And just from an intuition, so I don't have an intuition, I always think about zero temperature. So is that, do you think it's going to be a massive challenge or not? And if yes, is it more because you have to change a lot of code and develop a new method, or do you think it's computationally much harder, or is it easy?
Yeah. So, so it is not really about the coding, but it's mainly about the computation. It's still mainly about the entanglement. So there has been a work by Stoudemire. They using an algorithm called METS, METTS, to it's an algorithm combining the tensor network and Monte Carlo, and to try to address this finite temperature issue. But the problem is that most of these finite temperature methods, they start from the infinite temperature, and they're trying to lower the temperature to the ground state. And for the lower temperature, the required bound dimension would be larger. It's just like an NCETA method, also in the same way. Like in the infinite temperature, the density, the finite temperature density matrix would be like a product state of MPO. And if you lower the temperature, you increase the entanglement by the quantum fluctuation. So the problem is that it's difficult to really lower the temperature down to the transition on a large system size. Yeah.
So you'd need much larger bond dimension than you'd need at zero temperature, probably, like for the MPO than you need for the MPS right now.
Yeah. So what they did is to consider a fairly small system and allow them to go into the low temperature. But then the system is kind of too small to really see the transition because yeah. So it would be, I don't know, it would be interesting to see an infinite algorithm, whether they can, go into the lower temperature, lower than the transition temperature.
For sure. Thanks. Yeah.
Yeah.
Okay, so do you have any questions or comments? Okuni-san, please.
Yes, so may I ask about stripe order?
Yes.
So the stripe order you showed in your talk
Mhm.
basically has a commensurate wave number, but I wonder if stripe order with incommensurate wave number also possible. So
Mhm.
can you find, do you find any signature of such stripe order with
Yeah.
incommensurate wave number in your computation? Because if the system has a incommensurate wave number, the convergence of the DMRG computation usually becomes very bad. So
yeah. This is actually a very good question. But so in this, in the pure Hubbard model with our any T-prom, we always find this commensurate stripe wavelength. But with negative T-prom, we actually found an incommensurate wavelength. And we are still trying to understand. But the first thing is that so with negative T-prom and with higher doping, we'll see kind of almost superconducting state, and then the whole density is pretty uniform. So it's not like a strong stripe state here. And also the spin is almost, it's very small. The spin expectation value is very small. So in order to see this kind of stripe behind the state, we need to apply a magnetic field on one of the edge, on only one of the edge. Then we can see that the spin responds all to the Bach. And from there, we can see that when you apply the pairing field, then the stripe order can change, like from the commensurate to the incommensurate. And it can actually, then that is, there's some detail I could not explain. Actually, this different state would have different stripe order, and then this blue one, the ground state, the DMRG found is the commensurate, but the other two are incommensurate.
So
yeah,
the DMRG computation looked at some commensurate wave number.
Yeah. I think this is because the commensurate one would have smallest entanglement. I believe this is the reason, but I also want to mention that this kind of competing, but different stripe wavelength, they are very difficult to observe from the expectation value itself if we do not apply this magnetic field. So this can be, like in the experiment, it's possible this is not be able to observe. And this may implies, it's maybe not a stable stripe, but instead it's like fluctuating stripe, if we like to explain that way. So yeah, so there it is possible that there's some connection between the fluctuating stripe and the superconductivity in the negative T-prom region. But we are still trying to understand this.
I see.
Yeah.
Yeah, thanks.
Yeah, thank you.
Do you have any questions about or comment? Okay. Okay, if there is no question, let's thank the speaker again.